Good morning to all. Myself Jailal Sarkar, Department of Computer Science and Engineering, Tripura University. Welcome to our Faculty Development Program on Smart City and Internet of Things, sponsored by AICTE ATAL. Now we have a talk on knowledge of sensors used in IoT devices, intelligent sensor network, a smart city perspectives by Professor Siba Kumar Udgata sir. Professor Siba Kumar Udgata sir is currently a professor of Computer and Information Sciences at the University of Hyderabad, India, where he directs a research group focusing on sensor networks, IoT, wireless communication, and intelligent algorithms. He obtained his PhD from Bahrampur University. He worked as a research fellow at the United Nations University, International Institute of Software Technology, Macau. He has published more than 100 research papers in peer-reviewed journals and in international conferences. He has edited 10 international conference proceedings of Springer LNAI, AIC, SIST. He has recipient of the IBM SUR Award for the project Mobile Sensor Network-Based Rescue Management System. He has successfully completed 7 Government of India sponsored research projects in the domain of sensor network, IoT, and cognitive radio network. Now, I would like to invite you, sir. Please come forward and deliver your lecture, sir. Sir, please. Sir.
Yeah. So thank you, Dr. Abhishek. Thanks for your kind introduction and kind invitation. And I'm happy to be here. And good afternoon, everybody. And can I share my slides? I have the...
Yes, sir. You can share, sir. Your voice is audible.
Okay, good.
Yes, sir.
Just give me 1 minute.
Yes.
Yeah.
Slide is visible, sir.
Very good. I'm just a minute. Let me see if I'm able to change the slides or not. The slides are getting changed?
Yes, sir. It is changed, yes, sir.
Okay, very good. So again, once again, thank you all. Thanks for the invitation. So let me start discussing what we have been doing and what is intelligent sensor network, how it is useful in a smart city perspective, and things like that. So as Dr. Abhishek mentioned, I am Siba Udgata. I work for School of Computer and Information Sciences at University of Hyderabad. And most of you might be knowing University of Hyderabad is also an institute of eminence, and this award is conferred by Government of India. Right. So to put the perspective, in this particular some 80 to 90 minutes, I will be talking about how what is a sensor network, and then how the sensor network can be made intelligent with the embedded of intelligent algorithms and all that, and how these things can be put into a perspective of a smart city environment, right? So if you look into the what is a sensor, I think everybody knows that at this point of time. But just for completion, I would like to quote Wikipedia, where the Wikipedia says that a sensor is a converter that measures a physical quantity. It can be a temperature, it can be humidity, it can be pressure, it can be my heart rate, it can be my blood glucose. So it can be many things, right? So it's a physical quantity. So it can measure a physical phenomena and convert into a signal which can be read by an electronic instrument, mostly an electronic instrument. So what is that I'm trying to say here? In the first definition, according to Wikipedia, a sensor is a converter basically. So if you put a temperature sensor, it will convert the temperature of a room or temperature of the body to a equivalent signal. And what is that signal? That signal can be a voltage or a current or a light, whatever. So let's say it is a voltage because 90% of the sensors gives you voltage and all that, voltage and current. Let's say it gives me a voltage. If it gives me a voltage, that means what? With the degree of temperature, for example, if the temperature is 25 degrees centigrade, the voltage output will be, let's say, 2.5 millivolt. If the temperature becomes 26 degrees centigrade, the voltage output may be 2.6 millivolt. The voltage output may be 26 degrees centigrade. So the whole idea is that if I put a graph, so this is my x-axis. So in the x-axis, let's say I put the sensor value, so sensor parameter. So let's say this is x, and I get the millivolt. Let's say voltage is my output. So the voltage keeps increasing. So normally it should be like this. That means with zero temperature, the voltage output should be zero, and normally it is expected that it should be a linear function. So linear function means with zero temperature, the output voltage will be zero, and with 1 it will be something, with 2 it will be something, with 25 it should be something like that. But unfortunately, what happens is that when the function here is no more linear, it's not linear. So if I look at the characteristics curve of a sensor, it's not linear. Sometimes what happens, it becomes like this. Sometimes it becomes like this. Sometimes it becomes like this. So what does it mean? That means mostly the characteristics of the sensor curve is nonlinear in nature, number one. And number two, the nonlinearity is also not a constant over the entire operating range, right? So over an entire operating range, for example, if you look at this curve, right? So, and if you look at the temperature here, and this is the millivolt, if you look at this curve, this says that the sensing parameter or the millivolt that you are observed as an output is not a direct function of the sensing parameter, and direct function means direct, not a single function of the sensing parameter. So what happens? It gives one function here, it gives another function in this range, it gives another function in this range, it gives another function in this range, so on and so forth. Similarly, it can be like this, which is a simple nonlinear function. Now, what people do, I mean, what the manufacturers do is that they find that it is very difficult to characterize or to find a function and to embed that particular function into the sensing node. A nonlinear function becomes very difficult. So what they do, they find out the linear part of it. So for example, this part, let's say this part looks linear, right? So they take this part only and say that my sensor can observe values or can measure values only between these two. This is the range. So that means suppose this is 20 degrees centigrade to 40 degrees centigrade. So we say that my sensor will be able to measure temperature within the range of 20 degree to 40 degrees centigrade, and we call that as an operating range. So first, why do we have an operating range? Because during that operating range or in between that operating range, the sensor gives you accurate values, but beyond that operating range, the sensor gives you an erratic value. So the error will be more. So the first part is that we have sensors. The sensors will convert the physical parameter to a signal. The signal can be measured in terms of volts or currents, and there is a relationship between the sensing parameter and the voltage output or the signal output. But the problem is that mostly the sensor output, the function is expected to be linear, but it's not linear. So this is one important part. What I have just told, I have written it in the second paragraph. What is the second paragraph? A second paragraph says that a sensor is a device which responds to an input quantity, that is what is in x-axis, by generating a functionally related output. This is my functionally related output. For different functions, I have different type of things in the form of an electrical or optical signal. For example, it can be a light intensity, it can be voltage, it can be current. Now, a sensor's sensitivity indicates how much the sensor output changes when the measured quantity changes. That's the sensitivity of the sensor. So what is the takeaway from this slide? The takeaway from this slide is that the sensor is a device which converts a physical parameter to a measurable electrical signal. And the measurable electrical signal is a functionally related output of the measuring parameter. This slides courtesy Google Images. I have put it from different sensors actually. What it says that the sensors are of different types, sensors are of different sizes, sensors require different operating voltages, sensors varies in different cost, sensors also varies in terms of reliability. Just to give an example, the sensor size can vary from a kind of a dust, as small as a dust, to as large, as big as a room, right? So this is the variation in the size of a sensor. A sensor might require some nanovolts to operate, and a sensor might require some kilovolts to operate. A sensor might require a electronic circuit to operate, or a sensor may require some kind of a biological signal to operate. A chemical sensor. So chemical sensor means where you require chemical components or chemicals to measure the sensitivity of the sensor. So this slide says about different pictures, says that there are different types of sensor, there are different sizes of sensor, there are different principles of sensing, there are different cost factor associated with the sensing, and there is a different reliability associated with the sensing. Now, first let me talk about what is a smart sensor, what is an intelligent sensor, and what is a normal sensor, right? So first let us see, look at this diagram actually. I picked it from Facebook, somewhere in the Facebook actually. So what it says, look at this actually. And I take this code and define what is a smart sensor network and what is an intelligent sensor network. The difference between a smart man and a wise man is the smart man knows what to say, and a wise man knows whether to say it or not. I put it in the same context here, that I say that, what is the difference between a smart sensor and an intelligent sensor network? And smart sensor knows what to measure, but an intelligent sensor knows whether the measurement need to be forwarded to this server or to the cloud for some decision making or not. I repeat what I said. I said that sometimes what happens, I know what to say, but whether to say it or not, this is my wisdom. Similarly, when I talk about smart and intelligent sensors, many people say that a smart sensor knows how to observe the data, how to collect the data, what are the data to be collected and all that. But there are some more algorithms which sits on top of these measuring devices to take decision whether this data to be sent to the server, the cloud or not. So in this context, I would like to say that in a smart city perspective or in any sensor network perspective, the sensors will collect the data, but there should be a decision to be taken at the edge. We call that a decision at the edge or intelligence at the edge, to decide whether the decision will be taken at the edge, that means at the endpoint, or the decision will be taken at the server level or in a distributed environment or at a cloud level. So in this case, we say that okay, simply I say that okay, when you deploy sensors, thousands of sensors, hundreds, thousands of sensors in a city, and then try to collect the data, imagine the amount of data that is being collected and the amount of time that requires for the decision making, the delay in decision making, the latency in the decision making. So instead of that, people say that if I define an intelligent sensor network, some decision will be taken at the edge itself, some decision will be taken at the node itself, and some decision will be taken at the server itself or at the central level itself. So what is that is required? If a decision can be taken at the node level itself, then those data items, those data or those observations need not be forwarded, need not be communicated to the server. And you save a lot of energy, you save a lot of lifetime of the network, etc. So this is a standard difference between a smart sensor network and an intelligent sensor network. Now look at a bit of a block diagram of an electronic sensor system. What else happens in a conventional electronic sensor system? You have an input signal. What is that input signal? That can be a temperature, that can be pressure, that can be humidity, that can be whatever. So many things are there, right? So you get that parameter. So temperature is given. Your temperature sensor or pressure sensor or humidity sensor will measure it and display it. So what you have, let's say you have an infrared temperature sensor now. You see it in every mall, every place, etc. Right? So what they do when you enter it, they kind of aim at your forehead or something. They measure the temperature, right? So that's a simple conventional sensor. They get the input signal, the sensor will measure the data and display it. That's it. There is nothing else. No decision making, no processing, no controller, no saving, nothing. What happens in a smart sensor, like little bit enhanced sensor, we get the input signal, same TP, H, etc. Then the sensor will measure the voltage or current because I want to classify it. So the sensor will give you a signal. The sensor will not, I repeat again, the sensor will not give you a number, right? The sensor will always give you a signal, and that signal can be a voltage or a current or a light, etc. Now, based on the voltage output or current output or light output, you have to convert that to a number or to a digit, right? So the sensor will give me a voltage or current. Then we have an ADC. What is ADC? ADC stands for analog to digital converter. So if I get a signal like this will be converted. So this is the peak. This will be converted to 25 degrees centigrade. So this conversion is done by the ADC, analog signal to digital. So voltage, current, etc. are analog signals. ADC means analog to digital converter, that will get the digital data. What is the digital data? That 25 degrees centigrade or 26 degrees centigrade or pressure equal to this many pascals, etc. So that is the digital data. Then this data comes to a microcontroller or a microprocessor. So in the node itself, now look at this. This is my node. Now in the node, I have a sensor, I have an ADC, and I also have a processor, a microcontroller processor. So this microcontroller can do a little bit of processing. Then either it can display the data or it can even communicate to a server, depending on the requirement. So what is a smart sensor and how it is different from the conventional sensor? In a conventional sensor, we only deal with the sensor. In the smart sensor, we have a processor, we have a ADC, analog to digital converter, and we have a communication module also. So this communication module will either communicate using Wi-Fi or Bluetooth, etc., to communicate to a server or to a nearby device, or simply display it. Now, what happens in an intelligent sensor? Now, in the intelligent sensor, which is defined as in IEEE 14551, this is the standard as an intelligent sensor. So, what you do here, we have input signal. So, we have sensors. The sensor will give you voltage or current. Then we have an ADC, analog to digital converter, that gives you a digital data. Then we have a microprocessor. That means you go back to the previous slide. We have a microcontroller or a microprocessor here. That microcontroller or microprocessor can be Arduino, can be Raspberry Pi, can be ESP, can be anything, right? And then this is important. This part is intelligent. Now, then in that microprocessor, we have some intelligent algorithms, AI-based algorithms or machine learning algorithms, etc., which takes the intelligent decision. Now, the data comes, the ADC, the voltage or the signal comes, the ADC converts it to a digital format. The digital data will be fed to the microprocessor. The microprocessor, with the help of the embedded intelligent algorithms, will take a decision and then display it or communicate it to a server. So this is basically, so when I talk about intelligent sensor, this is an intelligent sensor. The only difference between intelligent sensor and the smart sensor is this intelligent algorithm. So when I have this intelligent algorithm, that intelligent algorithm defines that what is this intelligent sensor is. Now, what you do with this intelligent algorithm is very important, right? So what you do with this intelligent sensor is basically what you do with this intelligent algorithms, and we will discuss some of them here. Now, when you say that there is an intelligent algorithm here, who gives this intelligence to this intelligent sensor network, right? What is that thing that is responsible for the intelligence? Now, if you look at this, I have almost everything in computer science, math, and signal processing in electronics that is there, which gives the intelligence. So we have statistical signal processing algorithms, that is part of the intelligence. We have connectional, like artificial neural network, like deep learning, deep neural networks, artificial neural networks. So there are many other learning parameters which gives you an intelligence. So the intelligence algorithm here can be the signal processing algorithms, can be the artificial neural network, can be deep learning architects, can be fuzzy logic, I'll come to that, can be evolutionary algorithms like people might be knowing about genetic algorithms, particle swarm optimization algorithms, artificial bee colony algorithms, and there are so many algorithms. So all those algorithms, if they are embedded into this microprocessor, into the sensor node, that becomes an intelligent node. Now, next part is what is this fuzzy logic, right? So when I talk about fuzzy logic, I see that I'll use fuzzy model, right? Fuzzy set. Now, what is fuzzy? Fuzzy means, that means you have some data, right? Suppose I have a temperature data. Temperature data is 25, 26, 28, 30, 32, 35, etc. Right? Now let's say there is a rule. The intelligence is that if the weather is hot, if the weather is humid, if the weather is windy, and sometimes in between if you get a cold wind, then it is going to rain. Now look at the rule. The rule is that if the weather is hot, if the weather is windy, if the wind is little bit of cold, then it is going to rain. Now the output is that it is going to rain with a confidence of, let's say, 90%. But these are the three parameters: weather has to be hot, weather has to be windy, weather has to be humid. Now who decides whether it is hot or not? So this hot is a categorical data, is a characteristics data, right? Is a adjective, but that adjective comes from this value. Now 3032, will you say that 3032 is hot? It may not be hot in a summer season, but it is hot in a winter season. So what is fuzzy? With every data, there is a membership associated with that. What is the membership? The membership varies. This is my membership. It varies between 0 to 1. Now what happens is that if I say, what is the membership function of hot for temperature equal to 25 degrees centigrade? I say, let's say 0.1. What does it mean? It means that 25 degrees centigrade will be considered as hot only in 10% cases, not in all cases. So this membership function is equivalent to probability, right? In probability also we have a probability of 0 to 1. In membership also we have a membership function of 0 to 1. But I think I was attending one conference and I had one speaker saying that what is basically the difference between the membership function and the probability? The membership function or the fuzzy and the probability, they say that fuzzy is the uncertainty associated with the input, whereas probability is the uncertainty associated with the output. So if you toss a coin, whether you get a head or tail is the output of the event. Now, whether you will toss the coin or not, that's the input, right? So what is the membership function of tossing a coin or throwing a dice is fuzzy. But what is the output of the tossing a coin or throwing of the dice is the probability. So fuzzy is associated with the input, probability is associated with the output. Now, if I say, so what is fuzzy logic? Fuzzy logic means you take the input as fuzzy, input with some probability and then decide. But output is something different. So all these things are basically an intelligent parameter tuning, and this gives or this makes the sensor node intelligent. And in a smart city kind of an environment or in an application kind of an environment, we require a lot of intelligence to be embedded into the sensor nodes so that they make correct decisions. Now, so this is what I have already told you. So what is what is an intelligent sensor here? So the intelligent sensor concept is based on possibility of processing the sensor data, the flexibility to reconfigure the embedded function. Now I told you at somewhere, right? Look at this. I told you that the function can be like this also. So at a different range, the function characteristic changes. So the flexibility to reconfigure the embedded function also depending on the environment, depending on the sensor data, and also to aggregate external sensor data for better decision making. So basically what we are doing, we have a PC or a microcontroller, we have intelligent algorithms for the signal processing. So all you do to find out a better decision making, and that's what is called an intelligent sensor network for some kind of an application. Now this intelligent sensor, when I talk about embedding the intelligent algorithms also, there is a machine learning concept, because without the machine learning, it doesn't come, the intelligence doesn't come into that. So what is a machine learning? Again, I go back to my Wikipedia page where it says that machine learning is a branch of artificial intelligence. So that's where the intelligence comes from, which concerns with the construction and study of a system that can learn from data. I repeat here, it can learn from data. That means you give the data, it will try to fit a function, it will try to learn what will happen, what has happened in the future, it will try to reason out what has happened in the past, and based on that, it will try to predict the future. Now, one important thing is that the machine learning learns from the data. So data comes from the observation, data comes from the sensor. So when the data comes from the sensor, then the machine learning model will try to learn, it's a branch of AI, which will try to learn from the data. So if the data is wrong, the model will be wrong. Now what happens here? Now this is an important, a small slide, but an important slide. What you do is, I expect that in the past we collect a lot of sensor data, right? So from the last lot of sensor data, I take the sensor data and that I call it the training data. Why call it training data? Because I will train my system, I will train my computer to behave or to learn from the data. So I will take all the data and I train my computer. That means I will develop a model. So the learning will happen when you develop the model. So you have the past data. That means you have collected the data using sensors. And then based on that data, you train a model, you train a computer, you train an algorithm, so that now it will try to train the data. Now, what is training data? Again, look at this. So I have X, I have Y. So X is my independent variable, Y is my dependent variable. So I have these tables. So I have some, let's say some 100,000 data, 100,000 data items. Now, what is my idea? My idea that I will build a model. So what is the model? Basically a function, right? So I want Y equal to f of X. So I want to find out f, and this f comes from the model. I want to find out the Y is equal to f of X. F may not be a simple function. It's a very complicated, complex function. But I want to build a function fx such that when I put x1, x equal to x1 here, it will give me y1. When I put x equal to x2 here, it will give me y2. Now this y1 and this y1, this y2 and this y2 may not be exactly same, but the error is minimized. So what you do, we try to train the model by giving the parameter values of x and y, so that the model will try to build a function such that if you give x as an input to the function, it will predict the y, and the predicted Y is as good as the observed Y. If that is done, then my model is ready. Now, what is the future? In the future, if I get some X days in my future and I have the function, I put this X days here and I predict Y days. So this is what the future. So what is machine learning here? I learn the data from my past. It's a supervised learning model. I learn the data from my past where both input and output is known. And then in future, given the input, I will predict the output. That's the machine learning. Now, if you look at this slide, very interesting actually. In a normal programming, C programming, Java programming, C++ programming, etc., what do? You write a program and then you give the input data. So this is my input data. This is my input data. So I put my in my computer, I give my program, that is the executable program, then I give my input data and I get my output. That's perfect, right? This is what we do in a traditional programming. But in machine learning programming, what happens? You have the data, that is the x1, x2, x3, etc. I also have the output corresponding to that data, y1, y2, y3, y4 up to yn. What is this? This means that suppose I have temperature, I have pressure, I have humidity, I have wind direction and all these things, and the output is that whether it has rained or not rained. So what is my input? My input is pressure, temperature, humid, wind direction, wind speed. So these are my parameters x1, x2, x3, x4, etc. And my output will be whether it has rained or not rained. Now what I do, I give my data, that means I give my temperature, humidity, pressure, weather and all that. I give my output whether yes or no, that means rain has happened or not happened. And the computer will build a model, will build a program so the computer will find out a function here. So the computer will find out a function for x1, x2, x3 up to xk. That means these are the variables. So in future, tomorrow, suppose I find that my temperature is 28 degrees centigrade, my pressure is 75, my humidity is 50, my wind direction is north to south, and my wind speed is 60 km per hour. Will it rain or not? So this program will be built, and this program is nothing but this function. And when you give these inputs in future, it will tell you what will be the output. So what happens actually in the machine learning model? You give the data and you also give the output. The system will build a machine learning program for you. But in case of a traditional program, you give the data, you give the program, the system will find out the output. So in this case, look at this, the output comes here. The output is part of the input in case of a supervised machine learning model, whereas the program is an output, which is considered to be an input in a traditional program. So the basic learning is that you need to classify, you need to categorize, you need to solve problems, you need to predict, and few others. Okay. Now, so I had a small background about a sensor. I have a small background about the machine learning algorithms, and then I need to tell you about. Then let's move on. So when I move on, I see that there is what is that we have learned now, that the world is full of sensors. Whether you like it or don't like it, world is full of sensors. Even a standard mobile phone, a smartphone consisting of around 40 to 50 sensors. And you imagine how many mobile phones are there in a room or in a city or in a town or in a street or in a house. So you have those many sensors. Not only cell phones, you have surveillance cameras, CCTVs everywhere, right? So they are also sensors. Your GPS is a sensor, motion sensor, light sensor, your Alexa, everything is a sensor, right? So so the world is now full of sensors. Now what happens if you connect these sensors? If the sensors start communicating between each other, then that's a sensor network. Like a computer network, two computers or more than one computers are connected to each other. Similarly, in case of a sensor network, more than one sensor will be connected to a network. So they can communicate to each other. So that is called a sensor network. Now, if the medium of communication is wireless, we call it as a wireless sensor network. But if this wireless sensor network is connected to internet, now what is the advantage of an internet? Once it is connected to the internet, there is an internet protocol that comes into play. They are associated with an internet address, etc. So that I can browse it, I can get the data, I can connect to that particular node from anywhere in the world. So that becomes now Internet of Things. So this is the evolution. A simple sensor node, then a simple sensor, when the simple sensor is connected to a microcontroller, etc., it becomes a sensor node. Then the sensor nodes, couple of sensor nodes or more than one sensor node, when they communicate between each other, that becomes a sensor network. If the medium of communication is wireless, that becomes a wireless sensor network. If this wireless sensor network is connected to the internet, then it becomes an Internet of Things. So that's how we arrive at an Internet of Things. And as you know, Internet of Things is growing and growing at an exponential speed. And if I have to believe, that will be by around 2025, or people predict that by around 2030, there will be 50 billion. I repeat, 50 billion. 1 billion equal to 100 crore. 50 billion means 5,000 crore IoT devices will be connected to the internet, and that's the scale. And it is not only connected to the internet. When it is connected to the internet, 24/7, it will push data to the there. Now, where you store the data, zettabyte, petabyte, hexabyte, whatever byte you tell, this is not enough. So huge amount of data is coming up. How to store it, how to retrieve it, how to index it, how to query it. So these are the challenges that people are now facing. The when we discuss about, because the bottom line, as I told you, that the bottom is the sensor, that's the brick and mortar. The brick, if you want to construct a lot of building, etc., the foundation, the first thing is that the stone, the brick. The sensor is the basic building block of the Internet of Things, right? Now, what is the problem with the sensor? One, the sensor accuracy increases with the cost. Suppose you want to buy a temperature sensor which will be accurate up to just 25, 26, only up to integer number. It comes in, let's say 30, 40 rupees also. But if you want it to be accurate up to one decimal places, suddenly the cost becomes 500, 600. If you want it to be accurate up to two decimal places, it becomes 10,000, 20,000. If you want it to be accurate up to three decimal places, it becomes a lakh. So the cheap sensors are available, but they are not accurate, number one. Number two, when the sensors are cheap, the reliability is very less, because they are not very accurate. The reliability is very less, and they work in a limited operating range. For example, a temperature sensor will work only between 20 degree to 40 degree centigrade. If you want a temperature sensor which can measure up to 100 degree centigrade, the cost is 10 times. If you want it to be up to, let's say, 200 degree centigrade, the cost becomes 100 times. So the cost increases when the operating range increases. The reliability is less. If you want more reliable, then the cost is more. So now with intelligent sensor network, because see, if you want to develop an application in a smart city environment, right? If you talk about traffic management, if you talk about water management, if you talk about energy management, if you talk about anything, right? If you talk about pollution management, the basic building block is that you have to measure this data using a sensor. Now the sensors are not that reliable. The sensors do not work in a high operating range. The sensors are not very reliable. Then what do you do? So one is that if you develop a huge applications based on sensor nodes which are not very reliable, your application is going to fail. So first thing is that can you use whatever things are available in the market? But if you want a very highly accurate device, the cost is prohibitive. We cannot have a smart city kind of a environment using temperature sensors which cost, each sensor cost you 1 lakh rupees. You can't have that, because you want hundreds of thousands of sensors, so you can't do that. So the question comes that can computer science or the algorithm will fit in, and they say that you can increase the accuracy and extend the operating range. So initially it was working with, let's say, 20 to 40 degrees centigrade. Can you use the same sensor and make it up to 100 degrees centigrade? Then this becomes an intelligent sensor. So the main problem is that can you use them to increase the accuracy and extend the operating range? But what is the problem with the reliability, etc.? The main problems are these three: nonlinearity compensation, multi-parameter compensation, and drift. Just a minute, hold on. Excuse me. I'm in a class. Is it urgent? Can you come after 1 hour? I'll just read it. Yeah, thank you. So these are the three main problems. One is called the nonlinearity compensation, the multi-parameter compensation, and drift. Initially, in the first slide itself, I told you about what is nonlinearity compensation. That means what? So if you have a nonlinear curve or this type of a curve, then when the sensor changes, the value changes, right? It is not easy for me to predict what is the output. So because at different range, the function behaves in a differently, right? So what people do normally that they take this linear range and predict it. But can I find a curve? Can I find a nonlinearity compensation? Means if the curve is like this, can I find an inverse model and then superimpose it so that it becomes linear? And if it becomes linear, I can always find out what is the output there. So this is one. Now I'll come back to the multi-parameter compensation a little later. Then let's say what is drift. The drift says that with a graph, zero input, zero output. But that normally doesn't happen. It starts from here. So that means with zero input, there is some voltage that is present here, and that voltage is called the drift. You might have noticed it when you go to what do you call any kirana shop or somewhere. There is a electronic weighing machine. You look at that, there is something they have written that some value will be displayed. What is that some value? 10 or 20 or 30. The shopkeeper presses a button, that means that becomes 0. So if you see, there is in the weighing machine, the display will be, let's say, 10. The shopkeeper presses a button here, this display becomes 0. Now when it becomes 0, that means what? It makes it minus 10. The bias is minus 10. So whatever you weigh here now, that exact value minus 10 will be there, so that you get the proper value. So that means with 0, you should get 0, but if you get 10, you put a minus 10 here. But what is the main problem with that? This drift is also nonlinear. For example, if you want to weigh something between 10 grams, it will become 20 grams, and you minus 10, it becomes 10. But for 100, it becomes 111. For 1000, it becomes 1010 or 1020. So that means what? The drift also, the original drift here, whatever this much, the drift also changes, right? The drift also either increases or decreases over a time. So a linear drift correction, that means what we are expecting that this is my drift. So this part, so from here I will start measuring. So this is my correction. No, the drift also changes. And if you're buying tomato or potato, etc., that's fine. But if you're buying gold, etc., that is a very costly affair. Even 1 gram or 1 milligram change in your weight costs quite a lot. So what people have suggested that you have to do a drift correction, drift compensation. Now to do the drift compensation, if it's a nonlinear, then it becomes very difficult. So if that algorithm will be embedded into it, that becomes very costly, but at the same time. So that is the reason why you have a weighing machine in the potato shop or tomato shop, which cost you around 1000 or 2000 rupees. But the same type of weighing machine, principle is same. In a gold shop, cost you 1 lakh or 2 lakh rupees only because of this drift correction model. The third part is a multi-parameter compensation. What is multi-parameter compensation? I can give you some reasons actually. Let's say because you are trying to build a huge application in a city environment or something, you want as accurate as the input should be as accurate as possible. And unfortunately, they are not. So we need to talk about make them intelligent, make them compensate themselves so that they give you a correct output. If the output is correct, fine, you get a better result. You can build a better model. So in this case, what is multi-parameter compensation? I will give you some examples. Example number 1. Suppose, let's say you take any temperature, or there are many effects. For example, let's say I have a heartbeat sensor, right? So my heartbeat sensor is, I'm wearing a belt, and in the belt there is a heartbeat sensor which measures my heartbeat. So it counts how many beats per minute, etc. It is giving 75. Now, what is the problem with that case? There is no problem with the heartbeat sensor. But suppose I have to catch a bus and I see that the bus is leaving the bus stand and I have to run to catch the bus. The moment I run and catch the bus, my heartbeat increases, right? The number of beats increases to a greater extent. But that's normal because I'm running, that's normal. But your sensor there doesn't know that you are running or you are sitting or you are standing or you are sleeping, whatever. So the sensor, when it becomes 90, it gives you an alarm. Oh, your heartbeat is increasing by 25% over a period of 5 minutes. That is something abnormal. But the heartbeat sensor doesn't know that there is another sensor parameter, that is accelerometer, which measures the speed of the movement, is more. So what we're trying to do, that multi-parameter compensation means, say for example, I'm running temperature, right? So if it is a winter, so the weather also has an impact on my other body parameters. I give you another example. There is something here in this slide also. We have worked on a water quality sensor with Government of India. We got a project and we worked on that. So there are water quality sensors like pH sensor, like dissolved oxygen sensor, like turbidity sensor, like ORP sensor, etc. But each parameter is dependent on others. For example, the pH value is dependent on the temperature of the water. That means what? You take the glass of water, measure the pH value. Let's say it gives you some, let's say 8, right? The value is 8. But then you apply heat, the temperature increases. Let's say it becomes 35 degrees centigrade or 40 degrees centigrade. And you measure the same water, the pH value will become 9. So what is this? That means the same water at 20 degrees centigrade is giving pH value 8, and the same water at 35 degrees centigrade gives you pH value 9. What happens? What happens is that the WHO recommendation, World Health Organization recommendation, that you can drink a water if it is between, the value of the pH is between 6.5 to 8.5. So 20 degrees centigrade, you can drink the water because the value was 8. 35 degrees centigrade, you cannot drink the water because the value has become 9. So if you build a system in a smart city environment where you are monitoring the water quality and you say that, look, you give the advisory to the citizens that you drink the water is good or not good, you cannot do it. In summer it gives a different value, in winter it gives a different value. So we want to compensate the temperature and find out the actual pH value on a normal environment, right? On a normal temperature and pressure. For example, around in 25 degrees centigrade, what would have been the pH value given that at 35 degrees centigrade, the pH value is X. So that will give you that I should drink the water or not the drink water. So this is called multi-parameter compensation. And I tell you, the challenge is that every sensor parameter, every parameter is dependent on the other parameters, and the other parameter is also dependent on this parameter. So there is a very complex multiple interdependency between the parameters, and that restricts the accuracy of the sensor. So unless you put that multi-parameter compensation and do the sensor aggregation, this is not applicable for any large scale applications. So I have already told you what is nonlinearity compensation. Linear means simple curvature. This is linear. But what is nonlinear is this. So this is nonlinear. So this is linear. So if it's a straight line equation, it's linear, but we have already discussed about what is nonlinearity compensation. So nonlinearity in sensor is already there. In the characteristics curves, we see that there is a nonlinearity in the compensation, and sometimes the nonlinearity characteristics also varies with the range of the values. For example, it can be like this, then it becomes like this, then it becomes like this, like this. So this is also important thing. So the effect of nonlinearity that you are trying to measure the values of the parameters using the sensor in a wrong way, and that effect, that measurement error will affect the decision making there. So what happens actually, these characteristics are time varying because they vary with the time, because this is the range, and they are also influenced by other parameters, other environmental parameters, other parameters like whether I'm running, whether I'm, so for example, my heartbeat, right? My heartbeat normally increases a bit if I'm running fever. So if you run fever, because of the fever, your heartbeat increases, not because of the heart defect. So those effects will also be there, and that makes the system quite unpredictable, right? The value that comes actually becomes unpredictable because it depends on so many other factors also. So this is the problem of nonlinearity, and any intelligent sensor in a large scale application has to address it theoretically so that you get a better result. Better input means better output, better decision making. You know that principle, right? GIGO, garbage in, garbage out. So if your input is garbage, if your input is erroneous, then you will get erroneous decision making. But so that is what is the first part. Correct the input as much as possible. So for that, people use neural networks and all that. And I don't want to go back to the neural networks, etc. And I expect that some of you know the neural networks. Neural network is a black box where you give the input, you predict the output, and you know the desired output. So you know the difference here, that is the error. So this is my predicted output or estimated output. This is my actual output. This is my difference, that is the error. Depending on the error, you change the neural network model. And when you change it, give the input again and again and again. So after some iterations, your expected output and the actual output will be almost same. The error will be less. If the error is less within the acceptable limit, you accept that this model is now ready. This model is nothing but my function, right? So this is what the neural network normally does. Now let's say in the nonlinearity compensation model, compensation, we have two models. One is called direct modeling and another is called the inverse modeling. When I talk about direct modeling, it's very simple. So what I do, I take my X, all my inputs I take, and I give my system. What is the system? That hardware system, right, which measures the output. So the system, hardware sensor system will give the output, that is my function, and this function I take it and I give the inputs to the neural network also, right? I give my inputs to the neural network also. The neural network will also give me output. The sensor fusion will give me an output, and there will be an error here, and that error I will take and change the neural network. What happens is that once the neural network is trained fully, I don't need this sensor. I don't need this sensor means, I repeat again, this is my sensor output. This is my sensor output means with error and all these things. And I know what is the actual output of them. So the sensor output is there, the neural network will be there, and this neural network will compensate the sensor. So once I get this value, I'll take the neural network compensation output. So what I'm doing is, let's say this is my actual value, and this is my sensor observed value. So there is a difference between these two values. Now this difference, that is the error, I want to minimize this difference. I want to mitigate this difference. So this neural network and this system value, I try to find out what is the error and try to minimize the error. So when I minimize the error, when it becomes 0, that means I get whatever sensor output I get X. The same sensor output I will pass through the neural network and the system, and here I get the output and the error becomes 0. So that is a direct modeling. What is indirect modeling or inverse modeling? The inverse modeling is basically what we are doing. We are finding out, given f, x1, x2, etc. I find out what is the function f to predict y. But what is inverse modeling? Can I predict x given y? So y equal to f of x is direct modeling. X equal to f of y is the inverse modeling, right? So look at this actually. You give the input, that is the x. The system will give you something. You get the functional output here. Then this is the inverse model. That inverse model is f dash. So this inverse model, I'll put what is y dash. So I get this function. Let's say let me put it in this way. Let's say this is my temperature. This is my voltage, my millivolt that I'm getting here. This millivolt, I will give it to the neural network, and I predict what is the temperature. Now I know that the temperature here, this value is the error. Now this error, I take it, correct the inverse model, so that now given the millivolt, I can find out what is the temperature. Given the temperature, you can find out the millivolt. Given the millivolt, you can find out the temperature. So what is direct modeling? You reduce the error, and in the indirect modeling or in the inverse modeling, from the output you can get back the input also. So these two models are used to cross check the input at a proper way. Now this is another model. Like, I think the things are a little small. Let me just try to look at this. Now look at this. I don't know. I'll draw this actually. So look at my cursor here. This inverse model characteristics for temperature sensor drift compensation. So what is drift here? Look at this part. Look at this diagram. So this blue line, when this is 0, it should be 0 here. Now it is not 0. There is a drift here. Now look at this drift. If you look at the drift is also nonlinear. It is going like this, then it is changing like this, then it is becoming like this, etc. Now there is a green line here. So the green line here is this. This is the green line. Now what I do with the green line is basically like this actually. Let me plot it like this. So it is like this. My drift is here. It is going like this. And the green line is trying to do like this. So what happens actually, the drift becomes now this. So once you superimpose this green line, this is my green line, this is my blue line, and I superimpose this, so this becomes a linear drift correction. So then my problem is solved. So this is another one where I say that key. Now look at this. Okay. Now look at this. This is my this blue. The blue is the sensor characteristics. So the blue is the sensor characteristics. Look at the nonlinearity here. This green is the inverse function that we have generated. And when you superimpose this green with this blue, you get a linear line. That red is the linear line. Now, once it is linearized, my problem is solved. But what the companies do, or the standard conventional sensor do, so in this blue line, they find that, okay, there is a linear characteristics between 0.3 to 0.6. So they say that okay, my sensor will work between 0.3 to 0.6. Other things you manage. I don't want to do that. So this model, by this way, we can extend the operating range of the sensors. Now, first, what we did, I mean, any smart city environment, monitoring of the water level in the overhead tanks of the societies, individual homes, etc., is very important, because there is a lot of water wastage because of water overflow and all that. Now, what the normal method so far people are trying to do, or so far the available things are there, or available things are the market. That look at this diagram. This is the way the people do it now. So there is an overhead tank, water comes here. Now they put a sensor. Now what is this sensor? This sensor is actually ultrasonic sensor. What is this ultrasonic sensor? The ultrasonic sensor emits waves, ultrasonic waves. What ultrasonic wave is a sound wave. So a sound wave comes here. Ultrasonic means you cannot hear it, right? So a sound wave comes here. When it gets a water surface here, from the water surface, it gets reflected, right? So sound waves goes. Wherever it hits the water surface, it reflects and then comes back. So my ultrasonic sensor here will send the data, will send the wave and receive when it comes back. So this is called this round trip time, or we call it as a time of flight. Now, because I know what is the speed of the ultrasonic sound, I know what is the speed of the ultrasonic sound, I can find out what is the time taken for this round trip, and then so time taken multiplied by speed of the sound divided by 2 is the height. So this is the height. Now, once this is the height, I know what is the height of this tank, and I know what is the height of this empty space. So I know what is the water level here. That is the principle what people are doing, and it's perfectly fine. I have no problem with that. But if you look at a larger application, right, then what is the problem as of now? Now this ultrasonic sensor is also fitted with a Wi-Fi module so that you can send the data to a server, and then you can, in the dashboard, people can see where the water is overflowing and all that. But the basic thing, the fundamental brick is that this sensor and this principle, it will send a signal, the signal comes back, you know the speed of the sound, and you know the time of the flight, it will measure the time of the flight, then time of the flight multiplied by the speed of the sound divided by 2 is the distance, and you know this height of the tank, so you can find out what is the water level. But the problem is, I repeat, the problem is that the speed of the ultrasonic sound heavily depends on the temperature and humidity of the medium. It also depends on the gases, carbon dioxide, nitrogen, etc. But it heavily depends on the temperature and humidity of the medium. If the temperature changes, the speed of the sound changes. If the humidity changes, the speed of the sound changes. And I tell you a small example here. For example, the speed of the sound, what we normally do in the calculation, what people do is that 340 meter per second. But when the temperature is very low, for example, with the temperature equal to 5 degrees centigrade and relative humidity 0, you have to multiply it by 0.91. That means 9% less. 9% less. 9% means the speed of the sound changes by 9%. So 9% means 9 3 are 27, almost 30 meter per second. That means it becomes 310 meter per second. So the whole idea is that there is an 18% error. I repeat, there is an 18% error between temperature 0 degree centigrade to 100 degree centigrade and relative humidity 0 to 100. There is a difference of 18%. That means what? The speed of sound changes by 18% maximum depending on the temperature and humidity of the medium. Problem number one. Now that means what? The speed of the sound, what you are taking 340, now varies between 290 to almost 440. So if it is 440, then your distance calculation is erroneous because you have calculated the distance depending on 340, but the actual speed is 340. So there is a much difference actually. So what happens actually, the water level is actually up to here, but you monitor, your sensor says the water level is here. So that means what? This much of water will overflow. Or there is no water here, but the sensor says that this much of water is there, so that your pipe will not start. So there is a lot of problem because there is an error. So what we did is that we tried to compensate this temperature and sensor, temperature and humidity on this measurement, and tried to make it more accurate, so that accurate decision can be taken at a city water supply model. So that's the idea. And if you look at this graph, it says that this is nonlinear. This is also nonlinear. So it's a three-dimensional nonlinear graph, means that the dependent on the temperature and humidity is also not linear. This is problem number one. The problem number two is that what you have in this part, I repeat, in this part you have the temperature and the humidity. That means you are measuring the temperature and humidity at the top of the water tank. But because it's a water tank, the humidity near the water is more, the temperature near the water is less. Whereas the temperature at the measuring point at the top of the overhead tank is more, humidity is less. So when it travels, when the sound wave travels, there is a gradient of temperature and a gradient of humidity which you cannot measure. So we require a kind of a machine learning intelligent model to compensate this, just not temperature and humidity. The physics people cannot do it because there is a gradient of temperature in the medium, there is a gradient of humidity in the medium, and I need to compensate that gradient also without measuring it. So that's a problem, right? So we tried to do it, and I have already explained you find out the time of flight, you find out the velocity multiplied by time of flight, we have divided by 2 is the distance, and this distance, this is my water tank, so this much of water is available. So that is fine. But this is the velocity of the sound, which is erroneous. This depends on T and humidity and other factors also, but mostly on temperature and humidity. And because it depends on temperature and humidity, this V value changes. If the V value changes, the D value will change. If the D value changes, everything changes, right? So your entire decision making changes. So this is a simple ultrasonic sensor. This goes, hits a subject, comes back, and then we did all these things. So that's a simple experiment. Now this shows that, look at this. This shows that this is how the changes. Look at this: 320, 330, 330. This is my normal way of this is my speed of the ultrasonic sound. But when you have temperature and humidity, it can go up to this, right? So this is the difference. This is the, look at this, up to 330, something up to 330. When you change it, right, it goes up to 440. So this range, that means the values can change between 330 to 440. If it changes in that way, that means that's the bigger change. Look at this, that's the bigger change. If there's a bigger change, then that will have a bigger effect on the V, and then it will be compensated. So we did some experiments. So this is an University of Hyderabad overhead tank. We put this water sensor, and this is not difficult actually. Everybody does that. But what is important is that we put this intelligence compensation into that. So you used a DHT22 sensor, which is basically a temperature and humidity measuring sensor. You collected a lot of data during winter, during summer, during high humidity days, during low humidity days, and all that. When the water overhead tank is full, then when the overhead tank is empty, when it is half full, all sorts of. We did it for almost 6 months, right? Then we found that there is a distance measurement uncertainty there. That is already there, right? I have already explained that there is a distance measurement uncertainty there because the temperature and humidity are changing. And we have found that the temperature and humidity are changing. For example, in an overhead tank between 100 to 500 centimeter, we found that the temperature is at the top is 500 centimeter depth. This is the changing. Humidity is changing. So because at the top position, this is the temperature and humidity. In the middle position, look at this. At the top position, the temperature is 24, humidity is 71. When it goes in the middle, that means in the middle of the tank, the temperature is 23.5 and humidity is 72. It is increasing. At the water level, nearer to the water level, the temperature is 23 and the humidity is again 73. That means what? There is an increase in humidity when you go below the overhead tank, and there is a decrease in temperature when you go down this. So this is for 100 centimeter, that means 1 meter tank. So we went up to 5 meter tank actually. It's a huge tank. So we find that there is an uncertainty in the measurement. Now we did it. I mean, don't worry about this result. Now look at this result. We found that remember the error was almost 18 to 20%, but we found that between 2 to 100 input range. That means if the water is only 2 centimeter or 98, 100 centimeter, etc., the error is only, the mean square error is only 0.03. I repeat, 0.03. So the actual water level is, let's say, 100 centimeter. At best, I'm getting 100.03, which is almost negligible. Earlier, we used to get 110, 120, 115, etc. Between 101 to 200, when it increases, there is a slightly more increase, but still it is 0.08. And maximum, that means up to 5 meters, I get an error of 0.23. That means if the tank is measuring up to, let's say, 450 centimeter, water is there, 4.5 meter water is there, I am getting maybe 4.523 water is there. Another important thing I want to say that if you look at this, the operating range of the ultrasonic sensor which you have used, it specifies that you can measure between 2 to 400 centimeter only. It says you cannot measure beyond that. But with this nonlinear compensation, we could go up to 401 to 500. That means what? Between 0 to 400, the company says you can measure only up to 0 to 400. With algorithm, we could extend up to 500. That means we can extend the operating range by 25%. But if you go for a new sensor which can measure up to 500 centimeter, it is almost 10 times costlier. So that's the idea of this particular work. There are a lot of theory, there are a lot of algorithms and all these things, and I don't want to discuss all those small things. So this is a paper which we published, a novel ANN based adaptive ultrasonic measurement system for accurate water level monitoring, and this is published in IEEE Transactions on Instrumentation and Measurements. This is basically the idea where we tried to say that in a city, in a large scale, we implemented it at University of Hyderabad, but in a large scale, in a city-like applications, where you have to monitor hundreds, thousands of overhead tanks or water levels, then we require a very accurate water level monitoring because every drop is precious. So if that is the case in a city environment, then we should implement this, monitor this, and take a better decision. And that's the paper which published in IEEE Transactions. Now there are another things like we have intelligent load balancing, right? In a city network, when you put hundreds of thousands, let's say Hyderabad or Delhi or Guwahati or something like that, then you have a huge amount of sensors, hundreds of thousands of sensors are there, and they will be collecting the data and sending it. And remember, all these sensors are mostly battery powered, and unless you do a load balancing kind of a thing, they will die very soon, and the operating cost, maintenance cost will be very high. So what we thought, okay, we'll do a kind of intelligent load balancing in wireless sensor network in a city kind of environment where large deployments are there. What are the two objectives? We want some intelligent algorithms for different tasks, maximize the network lifetime, and balance the workload so that some critical nodes should not die before the other nodes are there. For example, I have 100 nodes, or let's say 100,000 nodes. Some 5 or 10 nodes die because they do more work, and your entire network is down. That should not happen. So we try to balance the workload among the nodes such that every node lives to a maximum time. So the basic principle what you are trying to do is the division of labor. That means the task that is to be done by the sensor nodes should be divided almost equally as far as practicable. Now there are two ideas that I want to present here. One is called the data prediction using machine learning approach, and the other one is the multiple cluster head selections. So what is the data prediction? I will not give you the details. I will just tell you what is the concept that you have used. The concept here is that there is a sensor node that is deployed this is my node, which is deployed at some location, right? Some location is here. My server is here. Now what I do, this data continuously sends me data. This node continuously sends me data. So this is basically a time series data. What I do, but I take my past using machine learning and all that, I take my past data and try to predict what will be the next data. So for example, I have 1, 2, 3 up to K. Now taking this K data, I want to predict what is the K plus 1 data. So I develop a model. Now this model, I put it here. I also put it here. So there is a model, there is a software machine learning model that is there in the sensor node. This same model is also working in this server. Now what to do? The sensor will collect the data, K plus 1 data. The model will predict the data, K plus 1 data. So this is K plus 1 dash and this is K plus 1. K plus 1 is the observed data, K plus 1 dash is the model data. That means estimated data. Now, if there is no difference, not much difference, or the difference is less than the threshold between K plus 1 observed data and K plus 1 predicted data, that means you are able to predict the data, predict the output, or predict the measurement at K plus 1th instant based on the data of 1 to K. Now, what you do, because the same model is also here, the same model here in this server will also predict what is K plus 1 data, and wait until the data is communicated to this point. If the data is not communicated, that means the server assumes that the estimated output and the actual output, there is not much of a difference. So this server just creates the model output here and creates a K plus 1th record. Now, interesting. What is the output? What is that I'm trying to foresee here? I developed a model, a time series model, to predict what will be the next instance based on the K instance. Then I can predict what is K plus 1 instance. So I do the testing, I do the learning, the algorithm is designed, the model is designed. Then what I do, I put that model in this server. I put the model in the sensor node also. Now the sensor node will observe the data. The sensor node will also predict the data using the model. If there is not much of a difference between the predicted output and the observed output, the sensor node will not send the data. I repeat, will not send the data to the server. And what this server will also estimate the model and then find out that and wait for some time. If it doesn't get the data, it assumes that the data which I have generated is also same that is observed. Just create a record there. Now we tried this and we tried with Intel dataset, Intel Berkeley dataset, we tried with Chinese city datasets, etc. And we also tried with our own lab. We found that almost 89% of the time, I repeat, 89% of the time, the model output and the estimated and the actual output are almost same. That means 89% of the time I don't need to send the data to the server, right? So if that is done, then I extend the lifetime of the network to a larger extent. I use the communication bandwidth available to me very efficiently. So I don't need all these things. So imagine now 100,000 of sensors are deployed in the city, and then you are generating data in the server using the model, and the model is as good as the observed data. So that means you are saving 90% of the communication time, 90% of the communication bandwidth, 90% of the lifetime of the network. So your maintenance cost will be down, your communication cost will be down, your latency will be down, everything is fine. So that is one approach we followed for data in a large scale deployment in a smart city environment, that you have to predict the data. The other thing is that we have multiple sensors. We call it a multiple cluster head selection. Yeah. So we have a multiple cluster head selection. What you know, in every sensor network, there are many clusters, many clusters here. There are many clusters. Now each cluster will be characterized by a leader, and the leader will be communicating, will collect the data from the members and communicating to the server. That's a hierarchical model actually. Now, what we found that in a there are multiple servers actually, right? There are police department, there are fire departments, there are weather forecasting departments, there are many other departments, government departments, and they need data from the sensors. Now we have deployed these sensors, and each sensor node is fitted with multiple sensors. Now, what we try to do is that can we, instead of having one head per cluster, can you design multiple cluster heads? This is one head, this is also another head. So this head, one head will be responsible for fire department, another head will be responsible for police department, another head will be responsible for traffic department, another head will be responsible for mobile department, and each head will send the data to different servers. So in that way, you are actually balancing the load. So that's the idea. So these are the two ideas we have done, and also did some experiment, etc. I think I can skip over quickly because I've already. So it reduces the amount of data transferred, right? It uses the radio to communicate. So the communication requires a lot of energy. So the communication energy also comes down. So many things, right? So this is what we have done. And I will tell you that in some cases, in one particular case, even got up to 99.63% in our lab that we have done. But when we implemented in the standard datasets, etc., it comes around 89 to 90%, which is considered to be very heavy, very high. 90% of the time, I'm able to predict it accurately, as good as the sensor observation. And that's very interesting, right? So this paper we published in wireless personal communication, the data aggregation using different transfer for load balancing in periodic sensor network. So this is published in wireless personal communications, right? So you can always check that, but this is the idea behind that actually. Similarly, I told you about the multiple clustering. So grouping the network into a set of smaller networks is called a cluster. Each sensor in the group sends the data to the group or cluster representative, or we call it a cluster head. Now all sensor nodes may or may not be location aware to have similar capabilities. So what we do here is that we try to put a multiple cluster head. What is the idea? Idea that a single cluster representative takes up the responsibility of aggregation and routing the data within the cluster to the sink or the server, and loses its battery energy very soon. So what you do, there are many sensor nodes, and the score of a node is a weighted measure of the residual energy. So what you do is that there are many sensor nodes, and out of that you choose one as the head node. But when you choose one as the head node, suppose there is a score, right? So the score is 23.2 here, and this score is 23.1. So because the score is 23.2, this is elected as the leader, and this loses the rest. So this becomes an ordinary member. But what we see that there, and this may be 23.19. So 23.19 and 23.2 is not much of a difference. But because that is slightly more, it becomes the leader, and every other becomes the member. What we are proposing is that if there are multiple members with similar power or similar score, similar weight, etc., they also can become a leader, and they can take a bit of load from the main leader. So for example, in a department, you have a head who is in a large department. He is very, for example, in our case, right, we have in the University of Hyderabad, we have a large department, and the din of the head is overburdened. So what he has done, he has made 3 more professors, one in charge of the MCA program, one in charge of the MTech Computer Science program, one in charge of the MTech IT program, and one in charge of the MTech AI program. So what happens is that most of the decisions are taken by the professor at that level itself, as far as that particular branch is concerned. For an overall policy and other things, the dean takes care of this thing. So what he has done, within the cluster of teachers, within the cluster of professors, he created multiple cluster heads. So this is the whole idea about a multiple cluster head, where each cluster head will take up some responsibility and the load will be balanced. This is applicable when each cluster is of hundreds of nodes, thousands of nodes. For example, I told you about the, what do you call, the water monitoring, right? Water level monitoring in the overhead tanks. There are hundreds of thousands of water overhead tanks in the Hyderabad city, and where if you put each one in each area, let's say Gachibowli area is a cluster where there are more than 1,000 or let's say around 100,000 overhead tanks. Now 100,000 overhead tanks, if you choose one cluster head, it has to collect all the data and send it to the server, and that is too much, right? So we try to divide the data, divide the load among multiple cluster heads, and each cluster head can take some responsibility. And you don't tell me that yes, you can still divide into small clusters. No, if you divide into small clusters, within that cluster one more head will be there, and that head may not be as efficient as the group head, right? So we try, so if you put a small cluster, all the cluster nodes there, that may not be good. So we try to divide the load there. So this is the objective. The workload will be a representative of the cluster. When there are a set of candidates, the CH are almost as good as choice of being CH for the cluster. So we do a kind of a load sharing. So I do all these things. We do everything. And this whole idea is again load balancing in wireless sensor network using multiple cluster heads. This is published in IEEE HITCON conference and all that. There are, I think how much time I have? Okay, I have another 15-20 minutes. So let's see. The same intelligent sensor is now kind of extended to soft sensor. So what is a soft sensor? A soft sensor is basically a software equivalent of hardware sensor. So what you do, let's say I have some sensors, let's say X1, X2, X3, and just listen to me, and Xn. Now what I find that if I know X1, if I know X2, if I know X4, if I know X6, then I can find out a function of that, and then I can predict X3. If that is possible, I repeat, initially what we did, we had n number of sensors for each parameter, X1, X2, X3 up to Xn. Then somewhere we found that, is it possible that I use X1, X2, X4 and X6, these four parameters, and predict and fit a model, fit a function f such that I can predict what is X3. If I can do that with a acceptable accuracy, then X3 sensor is not required. So X3 sensor is not required in the sense that X3 sensor, X3 hardware sensor can be replaced by a software model, and we call it as an X3 soft sensor. Now this can be used for multiple things. Number one, suppose X3 sensor is very costly, right? And so you can replace that X3 altogether and use a software instead of that, because it gives me almost accurate symbol. Then the second thing is that suppose I have a sensor at X1 location 1, I have a sensor at location 2, and I have a sensor in location 3. But can I predict what will be the sensor value between location 1 and location 2? For example, in a big room, I have a temperature sensor at the end of the room and one wall, and another temperature sensor in the other wall. Now, if I want to monitor them, the entire room, I should put 10 more sensors in between, right? Between a class level. So between this temperature to this temperature. So what I do, if this is my location 1, this is my location 2, I have a sensor here, X1 sensor only I have here. The value is V1 and V2. Can I predict what is the sensor node L12? The value at location here this location. So I use kind of a software model, and so how do I do it? I put some sensors here, I put some sensors here, I put some sensors here, and this is my location 1, this is my location 2, and I develop a model. If I want to predict this location, what should be my F1? If I want to predict this location, what is my function 2? If I want to predict at this location, what is my function 3? Once I know F1, F2, F3, then I can, knowing the value of X1, value 1 and value 2, I can put this value 1 and value 2 for this function and predict what is the temperature here. I can put value 1 and value 2 at this function and predict what is the value here, and so on. So I can avoid using actual hardware sensor at multiple locations between L1 and L2 by replacing a software sensor. So this is very important. So this is a soft sensor model by which, so what we do, now we find that in a city, I need to monitor the temperature, but I cannot put it at everywhere, right? So I put it at some points, so that, and what are the locations I put it, and develop a soft sensor so that for other points I can measure the temperature using the software model to as accurately as a hardware sensor. If I can do that, then I don't need many sensors actually. So this is the problem with sensor, which we have already discussed. Now, what is a soft sensor? The term soft sensor is a combination of the word software, because the models are developed in computer programs, and sensors, because the models providing similar information as hardware sensor. So soft sensor, also known as virtual sensors, so that is also known as that. So what is a soft sensor? Soft sensor used to predict important quantities or variables that are difficult to measure, that are very difficult to measure. So now we have many variables where we take some are easy to measure variables and some are difficult to measure variables. The difficulty may be because of the cost, because of the inaccessibility, you cannot go to that location and do it every time. So these are difficult to measure variables. So these are the two things. You have difficult to measure variables and you have easy to measure variables. Now the question is that, can I use these easy to measure variables or easy to measure locations to predict what is going to happen with the difficult to measure variables? If that we can do, then the soft sensor will replace the hard sensor there to a larger extent. But it's not possible for everything. For some sensors, for some parameters it is possible, for some parameters not possible. So wherever it is not possible, you can always go with a hardware sensor. But is it possible? So we also use the same, like you discussed that, right? In the water level monitoring, we try to use soft sensor for water quality monitoring. Now in a water quality, what are the normal water quality parameters like biological oxygen on demand, chemical oxygen on demand, chlorine, total phosphorus, and iron? Then there are temperature and all these things are there. Now we're trying to explore whether there is a possibility of soft sensor, developing a soft sensor instead of a hardware sensor. Now we found out one parameter called COD. COD means chemical oxygen on demand. COD is one parameter which is mandated by the environmental department that every sewage treatment plant should have it, because they don't want to pollute the environment. But that sensor cost around almost 2 to 3 lakh rupees, right? So the whole idea that we thought that that's an important thing, and there are chemistry lab based measurement also, you can do that, but that takes a lot of time. So the problem with COD that if you have a sensor that costs you around 2 lakh, 3 lakh rupees, that's also there are a lot of import restrictions. And second is that this is also not very reliable. Third, and if you do it in a laboratory, it takes a lot of time. So we thought that can we do it using machine learning model, intelligent model, etc. So what we did is that we tried this model. Look at the architecture here. There are some water bodies in the lakes and all that. So we put sensors there. And then we measure those values in the laboratory also, right? So we get DO, we get all these things. Then through the sensor, so we have a sensor node here. We get the data, and then using the data, we go to all the data will be stored in the cloud, and in the cloud we develop the machine learning model. We develop the machine learning model. Now, once the model is ready, then what I do, I take some parameters here and then do the live prediction of COD. So again, I repeat, I get the water, I measure the COD in the laboratory, I collect other parameters using the sensor. Then through the data acquisition, I take and go to the cloud. Using a machine learning model, I designed a model, a function for the COD. COD is the chemical oxygen on demand. Then what I did, I collect the other parameters except COD and started predicting the live prediction of the COD. So that's what we did here. And because we did it in our lab and other things, right? So the reviewers didn't like that. So they said we also did with it. So this is our model, and this one is a map of the Uttar Pradesh, and this is the river trajectory of the Ganga river. So during the Kumbh Mela, what the UP government did is that they put some dashboards, they put some sensors at different locations, and the data is continuously uploaded into a dashboard. You can see it in the website that what is the water quality of the Ganga river. So we downloaded that data also and then tried to model it. So what we did, we found that we measured DO, we measured pH, we measured temperature, we measured ammonia. So all these sensors are available. We also measured COD. But this measured COD we want to replace with a soft sensor. So what we did, we used these parameters to predict what is COD. So COD is represented as a function of all these things, right? So we did this, we found out a covariant matrix and all these things are done. Now we started estimating actually. So anyway, I could have done it. But look at this actually, this is the actual COD values. For example, at some point we found that the actual COD value is around 200. 198. Here also almost the same thing. This is the estimated COD value. If you look at this, I think the better is that you go to the next slide, where we say that okay, look at this. This is much better. So the blue line and the red line. So blue is the actual one and the red is the estimated one. And if you look at the towers, they're almost same. They're almost equal height. That means I'm able to predict COD value using the machine learning models and all these things, simulation, etc., which is as good as the actual COD values. That we try to do with the sewage treatment plant at our institute, etc. And we also validated it with the Ganga data, etc. So that's how we try to do, and there is not much of a deviation and all that. So this paper is, I mean, we published a paper. If you want to look at it, you can look at it in a much better way and refer to the paper actually. So this is published in IEEE Sensors Journal actually. So development of chemical oxygen on demand soft sensor using edge intelligence for a large scale deployment in a city environment. Similarly, the same model, I mean, it's not a much of a different model. The same model we have used for BOD. That was for COD, chemical oxygen on demand. This is for BOD, biological oxygen demand. But here the parameters are different, the function is different, etc. So here again, we try to use DO, temperature, pH, conductivity, the salinity, ORP, turbidity, the cloudiness of the water, and then we wanted to predict the BOD. So what we did is that first we found some kind of a relationship, did some principal component analysis, etc., and multiple correlation analysis, etc. We found that there existed relationship between these variables and BOD. That prompted us to develop a soft sensor actually. So we did the same thing. We applied various machine learning techniques. We found that this IBK, if you look at this correlation coefficient, is 0.9998. What is the correlation coefficient? We tried to take the actual observation and the soft sensor output, and that is almost same. 0.9998, it's almost same. The mean absolute error is 0.00007. That's the error in the observation between the actual value and the estimated value, so on and so forth. So if you look at this actually, somewhere the actual value is 1.218, the predicted value is also 1.218, no error. Somewhere it is 1.108, it is 1.107, just a small error, except somewhere here where it is 0.609 and 0.805, where the value is around 0.19. Some error somewhere, but that may be a kind of an outlier. But otherwise, this is the error. So we did with the same thing. We did with our own experiment. We also did with the Ganga data. Ganga data means that real-time Ganga data that the UP government has put up during the Kumbh Mela. Same thing. We also collected data from their side. What is their BOD? What is DO? What is pH? And all these things. We took whatever things are required for us and then predicted the BOD. And same thing. We also did same thing here. Also, this IBK data set gives me the best result. So in our experiment, what we did, we got the good result for this. And for the Ganga data experiment, what they have done with their sensors also, we also got the same result, right? So this is also the same thing. For actual value is 2.52, we predicted to be 2.53, 2.52, 2.46, 2.2, 2.3, 30.54, 30.60. So this is almost in the acceptable range actually. So this is also published in the Springer Journal of Complex and Intelligent System, machine learning based soft sensor model for BOD estimation using intelligence at edge. Okay, so I think that should be done, and then we have developed this system, put it in different lakes and institutes, etc. in Hyderabad. These are the locations where you have deployed those sensors and developed the intelligent sensor, developed the soft sensing model and all that. And this is a kind of a dashboard. When you go to this location, click it, you get what is the value there. You go to this location, click it, you get what is the value there, etc. I mean, this is simple. So some of these things we have implemented. We have put it in different parts of the city and all that, right? So some of our students here, he is Nagarjuna, he is Narsima, and they were going and deploying the sensor nodes in different places and all that. So I must acknowledge that there are two sponsored projects mostly that we have worked on. One project is that development of wireless sensor network based water quality monitoring system. We call it an Aquasense in a city environment. So that was the project sponsored by DST and followed by Ministry of Electronics and Information Technology. Then I got a chance to work with IIT Hyderabad and with the University of California and Stanford, etc., where they developed some sensors. So they developed COD sensor at University of California. They developed another sensor at the University of Stanford. We tried to develop soft sensor to match their quality and all that, right? So this is with IIT Delhi and all that. This is for city environment and this is for Yamuna River at Delhi. So we should thank them for that. So thank you very much. I'm done with my presentation. Thank you.
Thank you so much, sir, for sharing your sharing all the valuable information with us. Now, I would like to our participants, has there any question from any participants? So you can ask. So there is a question from Dr. Shunil that how we can measure a gas which have no others.
No, okay. So see, the gas order is one characteristics of the gas. The dielectric constant, the conductivity of the gas. There are many other properties of the gas, which the conductivity of the gas, right? The conductivity, how conductive is the gas, etc. So there are other parameters through which you also can measure it. Order is one characteristics of the gas, but there are other characteristics of the gas, and we have say constant of material, dielectric constant of the medium, etc. So I think that should be enough.
Okay, sir.
So
Thank you, sir.
even the color of the gas, even the color of the gas also. Yeah.
So has there any other question?
Yeah.
So thank you once again, sir, for sharing your valuable information such as
Thanks.
yes, sir.
Thanks for your invite and all that. And
Sir.
we must thank our sponsors also because they have given us some funding to work here. Good.
Yes, sir.
Yeah, good to be connected, Dr. Abhishek,
Yes, sir.
and keep in touch.
Thank you, sir. Thank you. Thank you, sir,
Thank you.
for sharing your information, sir. Sensors, smart versus intelligent, electronic
Yeah.
sensor system, machine learning, problem with sensor, linearity of sensors, effect of non-linearity, artificial neural network, and most importantly, your research work, sir. Thank you so much, sir, and take care of your health.
Thank you. Do take care.
Thank you,
Same
sir.
here.
Thank
You. I'm logging out. Yeah.
you. Yes. So, dear participants, this is the end of our this session. So, our next session will be start from 2 p.m. after the lunch period. Now, the feedback form will be shared with you. Please kindly fill it up and send back to us. Thank you so much.